5 billion. That is how many suns our sun, the colossal nuclear furnace that has powered every living thing on this planet for 4.5 billion years, could fit inside a single star. One star. And that star exists right now, burning somewhere in our galaxy, visible with nothing more than a decent pair of binoculars if you know exactly where to look. Astronomers have cataloged tens of thousands of stars across our galaxy and beyond, mapping their temperatures, their luminosities, their distances, and their masses. The Hertzsprung-Russell diagram, a tool independently developed in the early 1910s by Danish astronomer Einar Hertzsprung and American astronomer Henry Norris Russell, has given us one of the most powerful frameworks in all of astrophysics. Plot a star's temperature against its brightness, and a pattern emerges. Most stars, including our own sun, fall along a diagonal band called the main sequence. Stars on this band are in a stable phase, fusing hydrogen in their cores, pushing outward against the crushing inward force of their own gravity. This balance, called hydrostatic equilibrium, is what keeps a star alive, and it is what makes some stars far more spectacular than others. Our sun sits comfortably in the middle of that diagram, a G-type star with a surface temperature of around 5,778 Kelvin, fusing roughly 600 million tons of hydrogen every single second. Its radius stretches 700,000 kilometers. If you replaced a football with the sun, the Earth would be the size of a 2-millimeter peppercorn sitting 26 meters away. Even then, if you added up the mass of every planet in our solar system, Jupiter, Saturn, all of them, the sun would still be 743 times more massive than all of them combined. And yet, in the cosmic neighborhood, our sun is entirely unremarkable. Sirius A, one of the nearest bright stars to Earth, is roughly twice the size of our sun. Bellatrix, the left shoulder of Orion, the 26th brightest star in the night sky, is 8.6 times more massive, 4 times hotter, and 200 times larger in volume. Stars like Bellatrix are classified as B-type on the spectral scale, a system running from O, the hottest, to M, the coldest. The greater a star's mass, the more it compresses its own core, increasing the rate of fusion, flooding the star with energy and forcing it to swell to extraordinary proportions. But Bellatrix is burning fast. While our sun has a projected lifespan of 10 billion years, Bellatrix has already burned for 25 million and only has about 7 left. This is the cruel arithmetic of stellar physics. The bigger the star, the shorter the life. And that rarity means the truly enormous ones are difficult to find. So, science has been searching. But here is what no one can quite agree on. Just how large can a star actually grow? And somewhere out in the dark, past the edge of everything we think we understand about stellar physics, is there something even bigger waiting? The largest stars we have found do not just challenge our intuitions, they collapse them entirely. Physics suggests that stars cannot grow much beyond 150 times the mass of our sun without becoming so violently unstable that they begin destroying themselves from the inside out. The radiation pressure generated by fusion in an extreme mass star becomes stronger than gravity's ability to hold it together. The star begins ejecting its own material. At a certain point, it simply cannot hold itself in one piece. And yet, the universe appears to have found a loophole. When two massive stars collide and merge, rather than gradually growing through the slow accumulation of a gas disk, the resulting object can surpass what should be the mass limit entirely. The evidence for this possibility is written in the light of one of the most extraordinary objects ever discovered. A star called R136A1, located in the Tarantula Nebula, 160,000 light-years from Earth. R136A1 sits at the very top left corner of the Hertzsprung-Russell diagram, a position that represents maximum temperature and maximum luminosity simultaneously. It has been estimated to carry a mass of 265 times that of our Sun. Its radius is approximately 40 times larger. It belongs to a classification known as Wolf-Rayet stars, a rare and violent category of which only around 220 have been identified in our galaxy, though scientists believe as many as 2,000 may exist. Wolf-Rayet stars are in an advanced, late phase of their lives. They are shedding mass at catastrophic rates, throwing off plasma winds at speeds of up to 3,000 kilometers per second, losing as much as 10 solar masses every million years. R136A1 releases more light energy in 4 seconds than our Sun produces in an entire year. It will not exist for much longer. Estimates give it a remaining lifespan of perhaps 3 million years, less than a single blink in cosmic time. But R136A1, despite being perhaps the most massive star ever found, is not the largest, not by radius, not by sheer physical size. To find the true giants, you have to look not at how heavy a star is, but at what happens to a star when it starts to die. This is where the science becomes genuinely strange. On the main sequence, mass and size are closely related. Heavier stars are generally bigger, but stars do not stay on the main sequence forever. As a star exhausts the hydrogen in its core, the delicate balance of hydrostatic equilibrium begins to break down. Without the outward pressure of fusion to hold gravity at bay, the core starts to collapse. That collapse generates heat, eventually enough heat to ignite helium fusion in the core. But here is the critical detail. That same heat radiates outward into the star's outer shells, warming them to temperatures that previously only existed at the center. Hydrogen in those outer shells suddenly reaches fusion temperature too. The result is a runaway expansion. The star does not just grow, it blooms outward, its outer layers expanding to hundreds of times their previous radius, cooling as they spread, glowing a deep and somber red. The star has become a red giant. Our own Sun will undergo this transformation. Its current radius of 700,000 kilometers will eventually expand to a diameter of 300 million kilometers, large enough to swallow Mercury, Venus, and possibly Earth itself. That process applies to stars between 0.8 and 8 times the mass of the Sun. An existing example of this is Mira A, a red giant in the constellation Cetus. Its mass is only between 1 and 1.2 times that of our Sun, barely different, but its radius is at least 332 times larger. And Mira A pulses, swelling and contracting over cycles of 80 to 1,000 days. When those cycles align, its radius can reach as much as 402 times that of our Sun. But red giants are not the end of the scale. Stars above 8 solar masses undergo a more extreme version of this same process, expanding not into red giants, but into red supergiants, an entirely different classification, governed by different physics, reaching sizes that make red giants look modest by comparison. Betelgeuse is the most famous of them, a red supergiant in the constellation Orion, visible to the naked eye and familiar to most people as the slightly orange star in Orion's shoulder. Betelgeuse has a diameter of approximately 1.2 billion kilometers. That is over 700 times the diameter of our Sun. If placed at the center of our solar system, every rocky inner planet, Mercury, Venus, Earth, and Mars, would be engulfed. Jupiter would almost certainly be consumed too. And Betelgeuse is not even the largest. In the depths of the southern constellation Scutum, at a distance of between 5 and 10,000 light-years, sits UY Scuti. It is a red supergiant, not especially hot by stellar standards. In fact, around 40% cooler than our Sun, glowing that characteristic deep red. It is not visible to the naked eye. You need binoculars or a small telescope to find it. But inside its boundaries, you could fit 5 billion suns. 5 billion. That is not a metaphor. That is a volume calculation. The radius of UY Scuti has been estimated at approximately 1,700 solar radii, though uncertainty remains at these distances with multiple competing candidates. The star is 10 to 20 million years old and may have only a few million years remaining. There is even a possibility that, as it evolves, it could shed its outer layers and transform into a yellow hypergiant, an even hotter, brighter phase of late stellar life.
capable of ejecting the mass equivalent of Jupiter in a single explosive event and blowing clouds of oxygen, carbon, and nitrogen into space that stretch 10,000 AU in length, or 300 times the distance from the Sun to Neptune. These ejected clouds do not simply disappear. They mix with dust and gas to form stellar nurseries, the raw material from which new stars and eventually new planets and perhaps new life will form. Beyond UY Scuti, observations grow more difficult. WOHG 64, a red supergiant 160,000 light-years away in the Large Magellanic Cloud, is one of the only stars outside the Milky Way that has been directly imaged with any detail. Recent studies suggest it may have already begun its transition into a yellow hypergiant. In the past decade, it has dimmed measurably, throwing off material and becoming shrouded in its own ejected dust. Whether it is larger than UY Scuti remains unclear. Physics does provide a ceiling. It's called the Hayashi Limit, the maximum size a star of a given mass can theoretically reach. On the Hertzsprung-Russell diagram, this limit appears as a vertical boundary on the cool red end of the scale. A star that expands beyond the Hayashi limit for its mass finds that internal convection, the movement of hot gas through its interior, begins to dominate in a way that causes gravity to reassert itself, compressing the star back inward. Stars approaching UY Scuti's size are already close to this boundary. There may be a star slightly larger somewhere in the galaxy, but by the physics of stellar structure, it would not be significantly larger. Unless, as scientists honestly admit, we are missing something entirely.
So, what determines the size of a star exactly? The answer involves three interlocking factors: mass, evolutionary stage, and internal energy balance. Mass establishes a star's position on the main sequence and sets the pace of its life. A star with greater mass fuses hydrogen faster, produces more energy, and sustains a larger radius against its own gravity. But it also burns through its fuel more quickly. O-type and B-type stars, the hottest, most massive stars on the main sequence, may live only a few million years before exhausting their cores. Evolutionary stage then takes over as the dominant factor in determining physical size. Main sequence stars, including our Sun, are constrained in their size by the equilibrium between fusion energy and gravity. Once that equilibrium breaks, once the hydrogen in the core runs out, the star enters a new phase. Core collapse generates heat, new fusion processes ignite in surrounding shells, and the star's outer layers are pushed outward to extraordinary distances. This is the mechanism that produces red giants, and, at higher masses, red supergiants. Internal energy balance, particularly the relationship between radiation pressure, convection, and gravity, then sets the hard limit. The Hayashi limit defines the maximum radius a star can achieve before convection becomes dominant and gravity begins reclaiming the material. Stars like UY Scuti are near this boundary. The spectral classification system, O, B, A, F, G, K, M, from hottest to coolest, describes a star's surface temperature and, by extension, its color. O and B stars shine with a fierce blue-white light. G stars, like our Sun, appear yellow-white. K and M stars glow orange and red. The very largest stars by radius, the red supergiants, sit at the cool end of this scale. Deep red, enormous in volume, but not particularly hot compared to their smaller cousins. This explains an initially counterintuitive fact. The physically largest stars are not the hottest or the most massive. They are the most evolved, the most expanded, the furthest along the path toward their final moments. Their size is a symptom of age and dying, not of raw power alone. The rarity of these objects is also worth understanding clearly. Red supergiants are short-lived. Wolf-Rayet stars are rarer still, fewer than 220 confirmed in the Milky Way. The combination of mass, age, and the right evolutionary moment that produces a star like UY Scuti or R136A1 is sufficiently uncommon that we may have only found a handful of the true extremes even within our own galaxy.
Thousands of light years of obscuring dust and gas mean that many such stars may be invisible to us entirely with current instrumentation. There is something quietly unsettling about the scale of all this, and it is not what you might expect. The unsettling part is not that the universe is big. We are generally aware that the universe is big. The unsettling part is that within a universe so vast that individual galaxies are separated by millions of light years, and the cosmic web stretches across billions, even the largest stars are essentially nothing. UY Scuti, with its 5 billion solar volumes, would be invisible from a neighboring galaxy. It would not register. The Milky Way, home to hundreds of billions of stars, including some of the most extreme objects in the known universe, is itself just one of perhaps 2 trillion galaxies scattered across the observable cosmos. Our Sun, that colossal nuclear engine, 743 times more massive than every planet in the solar system combined, is equally invisible at those scales. And the Earth, the peppercorn, it is not even worth calculating. And yet, we are here, on this particular peppercorn, circling this particular average star, in this particular unremarkable galaxy, in this particular corner of a universe so vast no human mind has ever genuinely comprehended it. We evolved, somehow, from the atoms that were forged in the cores of stars that lived and died before our sun was born. The oxygen you are breathing right now was synthesized in a stellar explosion. The iron in your blood was forged in the collapse of a massive star. The calcium in your bones, the carbon in every cell of your body, stellar byproducts, all of it. When UY Scuti eventually sheds its outer layers in its final millennia, it will scatter those materials into space. They will drift and cool and mix with other clouds, and over millions of years, gravity will draw them together again. Eventually, some of that material will form a new star. Some will form planets, and on one of those planets, perhaps, under a yellow-white sun, something will look up and wonder where it came from. The largest stars are not just fascinating because they are large, they are fascinating because they are temporary, because their death is not an ending, but a redistribution. The universe recycling itself, moving matter and energy from one form to another, in a cycle so long and so vast that we can only observe the smallest fragment of it during a single human lifetime. There is a physics concept that applies here beyond the purely stellar. The Hayashi Limit is a boundary, the point past which a star can no longer hold itself in its expanded form and begins to contract. But before that contraction, before the inward collapse, there is a moment of maximum size. The star is at its most extended. It is also at its most fragile. And it is precisely at that moment that it begins seeding everything around it with the raw material for what comes next. That strikes me as worth sitting with. The largest things we have ever found are not permanent monuments to cosmic power. They are moments, impossibly brief on any scale that matters, where matter has expanded to its furthest possible reach before returning to something new. The bigger they get, the closer they are to transformation. We are, all of us, every atom in every body on this unremarkable peppercorn, the downstream consequence of that transformation. The universe built us from the wreckage of its largest stars. And it is entirely possible that the largest star we will ever discover has not been discovered yet, because our instruments cannot yet see through the dust that hides it. Perhaps it is out there right now, near the Hayashi Limit, swollen to a size that would humiliate UY Scuti, shedding its outer layers into space a few million years from the explosion that will scatter it across 1,000 light-years of galaxy. And when it goes, it will not be a loss. It will be a beginning. The universe is vast beyond comprehension, but that doesn't mean we stop trying to comprehend it. And sometimes, when you're standing under a clear sky with a pair of binoculars looking for a faint red star and scutum, you get the feeling that comprehending it, even partially, is one of the best things we do.